Alright, in the last video we saw how we could use a graphical method to find the solution to a pair of simultaneous linear equations. And in this video we're going to be doing some examples to solidify that knowledge. So we're given a set of lines here that intersect at the point 1, 3, and the idea is to find out whether this point actually is the solution to that equation. So one thing we could do is we could say, okay, so if we put the value of x here, we're going to have minus 1 plus 4, which is 3. And that's the same as the y coordinate here, so we know that it does satisfy this equation. Now for this one we can do the same, so that's 2 plus 1, that's 3, so this one also is satisfied by that set of points. So we can conclude that this is indeed the solution to that pair of equations. However, if we wanted to do a method where we are not required to draw the two lines on the Cartesian plane, we can just do the same technique we used in the last video, which is set both equations equal to each other, so we can solve for x. So now what we can do is we can move the 2x to this side, so we have 3x minus 3x on this side, and then 1 minus 4 is 3, so that becomes minus 3, and then we can divide both sides by minus 3, so x is equal to 1. And to find the solution for y, we just plug this value into one of those two equations, so we can use this one, 2 times 1 plus 1 is 3. So now that's how we would find the solutions without having to plot the two lines. Now for the next question, we're given these two lines that have a negative gradient and they both intersect at this point, minus 1, 2. So what we could do now is we could actually either plug those values in here to verify that this is indeed the solution to those two equations, or we could just use the same method again. So we're going to have minus 2 on 3x plus 4 times 3. It's going to be equal to minus 3x minus 1. And then we can actually multiply both sides by just 3. So that's going to be minus 2x plus 4 equals to minus 9x minus 3. And then on this side we can add 9x to both sides, so this becomes 7x. And subtract 4 from both sides, this becomes minus 7. And then that means that x is going to be equal to minus 1. And now from that what we can do is we can say, okay, so if we plug that value back into one of these equations, we're going to have y equals to, say, we use this one, minus 3 times minus 1, minus 1. This is going to be positive 3. That's going to be equal to 2. And that's how you would find those two solutions. And we can see that that corresponds to that point of intersection. Now for this third equation we have the same thing, but now both lines have different gradients. So let's have a look. We have the point 2, 2 is claimed to be the intersection between the two. So we can once again set up the equations. We're going to write minus 2x plus 6 equals to 3 and 2x minus 1. We could multiply both sides by 2 to get rid of that denominator. So this becomes minus 4x plus 12 equals to 3x minus 2. And now we could subtract 3x from both sides, so that's minus 7x, and subtract 12 from both sides, so this is going to be minus 14. So there, in the end, if we divide both sides by minus 7, x is going to be equal to 2. So that's correct. We already have that. And now we plug this value into one of these two equations. Let's choose this one. Minus 2 times 2 plus 6. That's going to be minus 4 plus 6, which is 2. And there you have it. That's the solution. So if you didn't really want to draw the two lines, you could simply do it this way, and then you can find both solutions to that set of equations. And that's basically how you would go about that. So you have seen a few applications of linear equations and how to use these concepts of straight lines to find solutions to systems of equations graphically. And this can be extended to other cases, so you could have a situation like this one. So let me just draw it like this. Say you have a set of axes x and y. And then you could have three lines. So you could have three lines that intersect at the same point. And if they all have different gradients and different intercepts, then what happens is this point of intersection between the three would actually be a solution to a system of three simultaneous equations. And if you had another one that passes through the same point, then you would have a solution to a system of 4 equations. But that's of course assuming that you could actually find a single point at which they all intersect one another. Because you could have a situation like this one. So for example, you have 3 lines, but only 2 of them intersect at different points at a time. So in that case, there's no unique solution to that system of equations. But this is something that you're gonna learn more about when you do year 12 mathematics and maybe even university mathematics. So we don't need to worry too much about that. At least you know now how to solve simultaneous equations when you have 2 equations, and there are different methods to do that.